Hey Calc BC, today we are going to start learning about lesson 7.8, Lagrange error bound. This is our second to last or penultimate, if you will, lesson in Unit 7. And we're finally coming back up to 10.12 in College Board's version of the units, Lagrange error bound. And if we take a look at the essential knowledge, we're going to be hitting this first point today. The Lagrange error bound can be used to determine a maximum interval for the error of a Taylor polynomial approximation to a function. So up until now, we have talked about alternating series error and how we can use the first truncated term in an alternating series to define a bound of the error. And a Lagrange error bound works for any sort of Taylor approximation, even if it's not alternating. So we'll take a look at that today. And it's going to be a little heavy on the reading, but I think by the end, hopefully it will make some sense. So let's switch over to the notes and get started. All right, here we go. 7.8, Lagrange error bound. I'm going to read a lot of this to you and kind of add some commentary as we go. Today, we will learn a way to find an error-bound approximation made with Taylor polynomials when the series is not an alternating series. Given that f of x is some power series in terms of x, these are terms that we should already know. We have a partial sum, which would be the sum of the first few terms of the series. We would know how many terms that is given a partial sum. The tail is a term that refers to the rest of the terms in the series after the partial sum. And the remainder is the number that you get by adding all of the terms in the tail, right? The remainder is everything that was left off in our approximation. So f of x is the partial sum plus the remainder, right? The remainder is all the terms from the tail. The error is the error that you make by assuming f of x equals the partial sum. So the error is the same number as the remainder. An error bound is a number known to be greater than the absolute value of the remainder. So if we make an approximation, we might not know the actual value of the remainder, but we might be able to bound the error to say, well, we're good within this amount. So now let's consider what Lagrange is credited with showing. The Lagrange remainder, or the error, is exactly equal to the first term of the tail, but with its derivative evaluated not at x equals c, the center, but at some number z, which is between c and the value of x at which you are evaluating the function. This value of z comes from repeated application of the mean value theorem. There is often no way of knowing exactly what z equals. But if you can find a number that is an upper bound of the derivative between c and x, then you can find a Lagrange error bound. I'm not expecting you to understand what all of that meant, but hopefully a little later on this page, it'll make a little bit more sense. So we have Taylor's theorem here. If we have, some certain number of terms, n terms, that we're including as our approximation, the remainder is equal to what we say as f to the n plus 1 derivative at some x value that we're calling z over n plus 1 factorial times x minus c to the n plus 1. It's actually not that different from the alternating series remainder. It still deals with the next term of the series that we are cutting off, the first truncated term. So the absolute value of the remainder is always less than or equal to this term with a maximum value of the y value. Okay, so this is where it gets a little bit weird. You might like, what is z? What is all of this that's going on here? First of all, I hope that if we just ignore this numerator for a second, the rest kind of makes sense. Or in other words, this part, we have n plus 1 factorial x minus c to the n plus 1. Hopefully that makes sense. That's just talking about everything that goes into the next term of the series, the n plus first term. The trick is, what are we plugging in as this derivative? And a lot of times, and the way that I like to think about this, I'm going to reword this so that we don't have to think about this like n plus 1 and z thing. I just think of the remainder has to be less than or equal to and it's often just called a capital M. So we could say m over n plus 1 factorial times x minus c to the n plus 1. And m then equals the absolute value of the n plus 1 derivative at some z. And what this really means is the biggest y value between x and c, and x and c are x values. So I made a sketch at the bottom of my page that hopefully will allow a visual here to help us. So let's think about it this way. Think about if we graphed the n plus first derivative of whatever function we're looking at here. So we've got the, let's say that we are looking at a Taylor polynomial that is up through n equals 2, right? So we've got the constant term, the first derivative term, and the second derivative term. Then this would be the third derivative graph. It's the first derivative that's cut off. So maybe this is the third derivative, and we're still centered at some c that we already know. It's whatever x minus c, whatever that c is. And x is then like whatever number we're actually plugging in for x. Because remember, x is just representing a number that we're trying to plug in. So then we look at this graph and say, okay, what's the biggest y value between c and x? And wherever that is, let me change colors here. Wherever that is, in this case here, the x value associated with that is referred to as z. However, we don't need to know what z is. Z is the x value. What we care about is the y value. We're talking about what's the maximum output or y value here of this n plus first derivative between c and x. So maybe we're lucky enough to actually know what that number is. We could plug that in as m. So this would be m. Maybe we don't know what it is, and we'll have to figure it out. But hopefully in some context, within some examples, this will make more sense. So let's just keep reading here. For n equals 0, Taylor's theorem states that if f is differentiable in an interval I containing c, then for each x in I, there exists z between x and c. I know there's a lot of letters going on here, but really, it all comes back to the mean value theorem, which you're not going to have to memorize that this is part of mean value theorem, but let's just keep going. When applying Taylor's theorem, you should not expect to be able to necessarily find the exact value of z. If you could do this, an approximation would not be necessary. Rather, you are trying to find the bounds for f to the n plus 1 derivative of z. So we're trying to find some upper bound of this capital M here. Okay. This is called the Lagrange error bound. Some of the AP grading standards for series problems use a different notation. In the series question from 2011, BC6, students were asked to show that the Taylor polynomial up through the fourth derivative minus the actual value of the function at 1/4 had to be less than 1 over 3,000. And you'd have to do that using the Lagrange error bound. So this is somewhere in this question, they were able to figure out that the maximum y value between 0 and 1/4 was 40. This notes doesn't tell us exactly where that is, but we'll see some examples down below of how we could get a number like that. And then everything else was just kind of plugged in. And then we see that that's less than the error 1 over 3,000. So that's how this would work. All right, so let's just try an example. I think the more that we try it, the easier it'll get. So let's see. We have a function with derivatives. All we know is the function value and the first 3 derivatives when x equals 2. Right, the third degree Taylor polynomial for f about x equals 2, and use it to approximate f of 2.3, give 3 decimal places. All right, so we need the third degree Taylor polynomial. That means we're going with the P3 of x. And lucky for us, we were given the first 3 derivatives, so we're going to be able to do this. The first value is just going to be 6. We're centered at 2, so that's good because we have f of 2. The second term is going to be, and this is coming all the way back from our Taylor polynomial notes. We've got 4 over 1 times x minus 2 to the first. Then we've got negative 7 over 2 factorial times x minus 2 to the second. And then we've got what? 8 over 3 factorial times x minus 2 to the third. If we wanted to get fancy here and kind of simplify our coefficients, we could end up with 6 plus 4 times x minus 2 minus 7 halves times x minus 2 squared plus what? 8 over 6, which reduces to 4/3, x minus 2 cubed. Okay. So we're going to use that to approximate f of 2.3. So we're going to say the P3 of 2.3, which is an approximation for f of 2.3. So if we have f of 2.3 is approximately P3 of 2.3, which equals, we're just plugging in 2.3 for each x. So I already went and did that on my calculator. You're not expected to do that by hand, but we're trying to give 3 decimal places. And I'm telling you right now that once you plug all of that in, you're going to get 6.921. If you want to check that on your own, you can. But let's move to letter B. The fourth derivative of f satisfies the inequality as given for all x in the closed interval from 2 to 2.3. Okay, that's going to help us with the capital M. We'll see that in a second. Use this information to find a bound for the error in the approximation of f of 2.3 found in part A. Okay, so we were given the interval from 2 to 2.3. Let's figure out why those numbers are important. If we take a look back at the original question, all of our function values were given at an x value of 2, and we were told that our Taylor polynomial is about x equals 2. That means that 2 is the C, the center. And notice that we are finding f of 2.3. That means, in essence, that that's what we're considering our x in this question. So when this first sentence here says the fourth derivative has y values that are all less than or equal to 9 for all x in the closed interval, that means that 9 is going to be our maximum y value, which we can plug in as capital M. So that means our remainder for the third degree Taylor polynomial, which still is considered to have an n of 3, is less than or equal to, and if we think back to that equation from the front, m goes on the top of this fraction, so we're given that that's a 9. The bottom is n plus 1 factorial. And then we have x minus c, which are both given, 2.3 minus 2 to the n plus 1 power. So we've just constructed the maximum of the next term in the sequence. So we have the 4 factorial, the x minus c to the fourth, right? That's as if we're constructing the next term in this series. We know the maximum of this derivative, which happens to be the fourth derivative, is a 9. So we're going to plug that in on top. So now what I'm going to do is type that into my calculator, 9 over 4 factorial times 2.3 minus 2 to the fourth power. And this equals, I already typed it in and I got 0.003037. Okay. Part C, use your answers to parts A and B to find the interval A comma B such that f of 2.3 is bounded. Give 3 decimal places. So all that's telling us to do is add or subtract our error from the approximation. So we're going to have 6.921 plus our error bound, and 6.921 minus our error bound. And we are told to round to 3 decimal places for each. So I'm going to say that we get 6.924 and 6.918. So our interval goes from 6.918 to 6.924. And our actual value of f of 2.3 has to be somewhere in that interval. Because that's how we bounded it. Okay, so part D, could f of 2.3 equal 6.922? Well, is that in our interval? Yes. So we would say yes, because 6.922 lies within our bounds of approximation, or the bounds of our error. Could we equal 6.927? No. 6.927 is larger than our upper bound. All right, hopefully that makes sense. Let's keep going. We've got one more example here, example 2. Let f be the function given by f of x equals sine of 5x plus pi over 3, and let p of x be the third degree Taylor polynomial for f about x equals 0. Find p of x. All right, we weren't given very much information this time, so we've got to construct this from scratch here. We're going to need, we're going to make a Taylor polynomial, and it's going to be third degree. We're going to need the initial function and the first 3 derivatives of f of x. So I'm going to write that out first. So we're going to have f of x, f prime of x, f double prime of x, and f triple prime of x. So we've got sine of 5x plus pi over 3. So I take the first derivative, I'm going to end up with cosine of 5x plus pi over 3 times the derivative of the inside is going to be 5 in front. The next derivative is going to be negative sine of 5x plus pi over 3, 5 times another 5, so we got 25. And then up next, we're going to have negative sine leads to negative cosine of 5x plus pi over 3. And we're doing 25 times 5, so 125. All right, then I need to be plugging in 0. So we're going to have f of 0, f prime of 0, and so on. You should be hopefully used to doing this by now. So we're plugging in 0 for all of the x's. And so this just becomes sine of pi over 3, which becomes root 3 over 2. Second one becomes 5 times 1/2, so 5 halves. Next, we have negative 25 times root 3 over 2. I'm going to have negative 25 root 3 over 2. And then we have negative 125 times 1/2. Okay, I'm ready to make my third degree Taylor polynomial. So we have p sub 3 of x equals root 3 over 2 plus 5 halves x plus, well, it's negative. So we have negative 25 root 3 over 2 over 2 factorial times x squared minus 125 over 2 over 3 factorial times x cubed. And if we want to make that look a little bit nicer, we can say it's root 3 over 2 plus 5 halves x. This ends up being minus 25 root 3 over 4 x squared minus 125 over 12, because 2 times 3 times 2, x cubed. Okay, so there we go. And then we get to part B, use Lagrange error bound to show that when we plug in x equals 1/15 into our approximation and into the actual function, the error is smaller than 1 over 1200. So what we need to know is the absolute value of the remainder for when n is 3. It's going to have to be less than or equal to some m over 4 factorial times x to the 4th. Are you with me so far? You should be, hopefully, because we know that c is 0, so it's just going to be x to the 4th. We don't need to worry about x minus c. We have a 4 factorial on the bottom because that's what the next term would have. And m needs to be the maximum potential y value when we're looking at the 4th derivative of f. So let's see if we can figure that out. M, we could say, has to be the absolute value of the 4th derivative at some unknown x value that we're calling z. And we're calling it z. We don't need to find z. We just need to figure out what is potentially the largest value between 0 and 1/15th, potentially. So let's just see if we can find f to the 4th of x. And by f to the 4th, I really mean the 4th derivative. So we can do that. We've got the 3rd derivative. So now we're going to find the 4th derivative. So negative cosine, we take a derivative, it becomes positive sine. So we have positive sine of 5x plus pi over 3. Negative 125, well, I'm thinking of it as just 125 now because I got rid of the negative, times 5, so it's going to be 625. So here's where we come up with a little bit of a trick. And my question to you is, what is the maximum y value when we have a sine function? Think about what a sine curve looks like. It bounces up and down, right? It's a wave function. And the y values kind of like bounce up and down between -1 and +1. So we could say that sine and cosine, and this is very important, you definitely want to write this down, sine and cosine automatically have a maximum y value of 1. So what that means is that therefore, we could say that m, the maximum overall y value of the 4th derivative, could be 625 times 1. We can replace this sine function with a 1. So therefore, it could be 625. So we can come back over here. And we could say that this is now going to be the absolute value of 625 over 4 factorial. We know that x is 1/15th in our error bound. That's the x value that we're plugging in. So we have 1/15th to the 4th. And if we plug that into a calculator, we're going to get 0.0005144. And 1 over 1200, which we're comparing this with, is 0.0008333. So if we compare those decimals, the first one is smaller than the second one. Therefore, our error, which we're saying is f of 1/15th minus p of 1/15th, is smaller than 1 over 1200. Okay? So the hardest part, I think, here is figuring out what m is. So hopefully that made sense. Sometimes you're given a graph and you just have to look for what's the largest y value between x and c. It depends on the question. So go ahead and give this a shot. Let me know how the practice goes. And as always, let me know if you have any questions. Thanks. Have a great day.